Hi everyone, it's me, Carolyn, and in this video we're going to be talking about one of the last um, hypothesis tests that we're going to be looking at for the semester. We do have one more to come, but that will be in our chapter 14 situation. Right now we're in chapter 13, and we're going to be looking at ANOVA, which stands for analysis of variance. Sounds really scary and all that kind of stuff because we're doing analysis of variance, but in reality, we're just going to be trying to determine if means are different from one another when we look at more than two. So you can use this for as many as needed. My example will have three, but we will get right to it and look at what happens. All right, I am going to share my screen and look at our guided notes. Let it adjust here. There we go. And we're going to be comparing three or more. Now, if we were comparing two, we would go back and use our techniques from chapter 11. And that's why if we have more than two, which happens, we want to use this ANOVA. And we will be doing a one-way analysis of variance. And ANOVA is analysis, the O is of, and the VA is for variance. Now, we aren't really looking at the variances, but we kind of are. You'll see it in the calculations. So first of all, our requirements. We have to have K simple random samples, one for each of the K populations. So if you have 12 different groups that you want to compare, you need to have 12 simple random samples. Now, these samples do not have to be of the same size. The one that I am doing does, but you can have them all different sizes. The larger, as we studied before, the larger your samples are, probably the better results you will get. We want to make sure that our samples are independent from one another. So making sure that the subjects in one group do not affect or aren't related to anything in another group. The populations are normally distributed. To do that, again, we want to make sure to have large enough samples, or make sure that we look at the curves and see that they are somewhat normal. Try to avoid outliers, because outliers could affect that normality. We want to make sure that they all have the same variance. The way we will do that is we will look at the variance of each of our samples and just make sure that there isn't one that is twice the smallest. So we'll kind of look at that. A note, just to kind of keep in mind, ANOVA is robust, meaning that if we have small departures from normality, it's not going to significantly affect the results. So when we're looking at being normally distributed, if it's close, we'll still be okay. So just kind of keep that in mind. So ANOVA is a pretty good tool for checking to see if means are the same or not. This test is quite calculation heavy. And luckily for us, technology, and we talked about this through other videos, technology is going to take a lot of that away from us. Because what we would be doing in here is looking at a lot of different variances. And if you remember how to calculate the variance of a sample, we had to take the mean and then subtract off each data value from the mean, square all those numbers, add them all together, divide. Very similar things done here, but more than once. So I will talk about the calculations to do in this procedure, but I will not be doing them. We will be using technology to do all of this process for us. I am not even going to go to the table for this one. We've seen the t-table, we've seen the normal, standard normal, the t, we've seen chi-squared. I think those are a good flavor of what's out there. So, but here's our hypothesis test, the 5 steps that we're going to go through. Step 3 is going to be quite extensive as far as the discussion. However, remember, we will be using technology to do the work for us. So first of all, our hypothesis, the null hypothesis, is that all of our means are the same. So mu1 is equal to mu2, all the way up to mu k, depending on how many we have. So you could have 7, you could have 11, you could have 3. Again, if you had 2, we'd go back to techniques talked about in chapter 11. The alternative is at least one of the population's means is different than the other. We would could go then further and do more analysis to find out, is that one different from each by doing a bunch of different 2x2s. So step 2 is to find that alpha level, and step 3 is to find our test statistic. And our test statistic is an F. So if we were looking at a new curve, we would be looking at our F curve. And our test statistic is found by taking our between sample variability and our within sample variability. I'll go into those in just a moment as to how we would actually calculate those. Okay, and to find these, there is a lot of stuff we'd have to do if we were doing it by hand. Okay, so the first thing we'd have to do is to find the mean of every sample and the variance of every sample. Okay, so for sample 1, we'd have to get X bar 1. We'd have to get its mean. We'd have to get the sample variance for that particular sample. We'd have to do this for all K samples. So now we have done a bunch of work. Then we have to find the mean of all the data. So add up every data value and divide by how many total data values you have. Some books refer to this as the grand mean. And we're going to label that just plain old X bar. Some will use more of a capital X. Here I just used just the lowercase x bar, but notice I do not have a subscript on it. The subscripts refer to the sample that they're attached to. And we're going to be then looking at the 2 types of variability. Okay, so the variability due to differences in the treatment groups, because you're doing a different thing to each group. So one group is going to get this, another group is going to get that. So there's going to be some variability between the groups themselves just because of the treatment that's done on them. There's also variability within each group due to the differences between people or between objects, whatever we are measuring. So this mean square error, that's what this is, mean square error, is our within the group variance. So to find that, we have to, it's kind of like a weighted mean, but we have to take n-1 times the variability for group 1, the variability for group 2, adding all of these up, and then we're going to kind of average those together to somewhat of an average. So we are kind of like getting all the averages of our variances, so to speak. If you look at this bottom, and you kind of rearranged all the pieces, we'd have N1 plus an N2, adding up all the first pieces. We'd have all those N's added together. And we'd also have 1, 2, 3, and we'd have K's. We could rearrange it just to get N minus K, where N is the total number of all individuals or things that we've got, and K is our group. So I could replace this whole bottom with just N minus K. I cannot do that to the top because notice these are attached to the variances and being multiplied. So we have to be a little bit careful on the top. Again, a lot of work. Okay. However, technology is going to do it all for us. All right, we also want to have the between sample variance. So this is kind of averaging this variances within each group. So remember the differences between people. Here we're kind of averaging between the groups. And this is where we're going to look at the X bars. So we're kind of doing a weighted average of the averages. So we're going to take that X1 minus our grand mean, that's the mean of everything. And we're going to do that to all of those pieces and divide by K minus 1. And I forgot part of my formula. These are all squared. They should be. I'll have to go and fix that on my sheet for you guys. So it will be correct on the sheet that is in Blackboard. I will square those and get that corrected. But all of those are going to be squared. So similar to calculating a variance. This is like a variance of all the pieces. And then we do divide by K minus 1. And again, to calculate our test statistic, we're going to take this thing, the between samples, and divide by the within samples. Okay, then we would go and find our p-value, which we will use technology. And the critical values we could do by finding using our F table. And our F table is a little bit more complicated because we have that between and within variability. So we'd have our alpha level, we have K minus 1, that's the denominator here, and we also have that N minus K, which is the denominator here. So it's the denominator of our numerator, denominator of the denominator. But again, we will use technology to help us on most of this. Then, of course, we decide and write our conclusions. So whether or not to reject, and then again, putting it in layman's terms back to the original problem so that the person can just arbitrarily understand what's going on without having to know statistics. That's the biggest thing, is we want to make sure our conclusion makes sense so that someone who doesn't know statistics understands what we just found. Okay, so here's my example. And I'm going to be looking at soybean yield. So we have an agricultural researcher wants to determine if there is a difference in the number of pods for each type of weed control. Okay, so the plots where these things were planted are going to be assumed to be equal. So they get the same amount of sun, same amount of soil content, so fertilizers, etc., same amount of rain or water. So that being equal, the only thing that's going to be different is how the weeds are controlled. Okay, and then they did some samples from the following. So we have the different type of weed control, our Liberty, which is a weed spray, no tilling, which just means you let your weeds grow, and chisel plowing is when you kind of go and plow between the rows. Okay, so we're testing again at alpha of 0.05. So here we are. We're going to do our 5 steps. Again, I will use StatCrunch to do most of it. This can be done in Excel as well. A lot of times Excel, to do these tests, we need to add in another small add-on with our data analysis package, and a lot of those things would then be incorporated in there. But that would be something for another video. Okay, so H naught is that our mean of Liberty is the same as the mean of our no-till. I'll just use NT, and the mean for our chisel plowing. So that those three are the same. We could have had different types of other, like we could have had other sprays that we were testing. We also are looking at, we have the same number in each of our samples. That does not necessarily need to be the case. We could have had 15 in one, 30 in another, 26 in the third. It does not matter. We just want to make sure that they are independent from each other, which we will assume in this case, and that they are relatively equal except for the thing we're testing. The alternative is at least one of these means is different than the others. Okay. Step 2 is our alpha level, which we decided was 0.05. Now, if I were doing this all by hand, I'd have to calculate the mean of each of these groups. I'd have to calculate the standard deviation for each of those 3 groups. I'd have to calculate that grand mean, and then I'd have to do those weighted pieces that we talked about, that in between, weight those variances, and then kind of do like a grouped average of the, like a standard deviation of overall averages kind of thing. Okay, but we're going to go to StatCrunch to get our test statistic, and then number 4, we will actually get the p-value, because I am not going to introduce the tables in this section, which is where we would get our critical value. And then we will also make our decision and write our conclusion. So I am going to switch over to StatCrunch here. And so, because I already put all the information in there. So I have our Liberty, our no-till, and our chisel plow. This one is relatively easy to do. So there's not a lot of buttons to click. But again, it's under our statistics. It is ANOVA, We are doing a one-way. So stat, ANOVA, one-way. Then we're going to select our columns. I'm doing a clicking and dragging. Whoops, come back here. Get rid of that. So click and I drag. So you see all three of them sliding over. And then all I have to do is hit compute. That fast. All right. So what it gives us is it does give us how many we have in each. I have 9 different pieces in each one. There is the mean of each one. So we do have different means. Notice this one is a little slower than the others, but we don't know if it's statistically smaller. And that's what this whole test is about. We do have our standard deviations. A 3 is our smallest. Doubling 3 is about 6.4, 6.5. If I go a couple more digits, notice these are not bigger than that. So we can assume that they do have equal variances. And actually, those are standard deviations, so we'd have to, yeah. Anyway, so here's all of these pieces that we're talking about. So there is our F statistic. So that's our test statistic, that 3.7. 3.7, and I'm just going to go 7.7. Our p-value is 0.0378. We do have the MS, the numerators, and these are those mean square errors, kind of right in here. That's where this is calculated. So by taking this would be in the numerator. Here's that denominator. So taking that 74.4 divided by that, and we get all of our pieces. So back to our regular guided notes. We've got our information. We can now finish up and write our conclusion and make our decision. We have it refresh here. There we go. There's our F stat statistic, our test statistics, which gave us the p-value. Thank goodness for technology. We wanted to know, is that p-value less than our alpha? And yes, it is, which means we will reject. Okay, which means there is enough evidence to show that one of these lead controls leads to a different average. What are we counting? Pod count. That sounds good. Now we don't know which one it is. We did see the one was smaller than the other. There was one that was larger than the other two. You could do more analysis to say, is that third one, that one that we saw, smaller than the other two? And you could do like test that one against each one to see if it is indeed smaller. But as a farmer, when you're looking for pod count, you actually want larger. So we'd kind of want to make sure we'd look for the largest one. And there might not have been much of a difference between our Liberty and our no-till. If I remember correctly, those two were pretty close together in the average. But I'm going to stop my sharing right now, come back to me. This kind of does the analysis of variance. And this used to be a really, really difficult section to teach. But technology has taken away all of that work for us. So it isn't so bad anymore. We've already set up all of the preliminary stuff by learning how to deal with the p-values, how to control, to make our decisions, write our conclusions. So by the time we get to this chapter, we just kind of keep going with the same things we've already done. So the only difference is technology does do all the work for us. If this didn't happen, this test is very, very calculation heavy, but that is done for us. So anyway, I'm babbling here. I will talk to you guys all in the next video. So have a great day.